Now we're going to kind of talk about kind of like the shape of data, and specifically, we're going to focus in on one kind of distribution of the data. So let's go ahead and talk about distributions. Again, we're doing a brief overview of this. Those of you that are going to continue into STAT 2023, we're going to dive a lot into this and talk deeper about distributions and things like that. So let me show you some distributions and we can talk about them. So sorry that some of these pictures are a little blurry, but these are some of the distributions that we run into. So this is called uniform. Okay, the reason it's uniform is because every kind of, and there are like bars in here that you could have, but every bar is all the same length. It's uniform across the board. Okay. So when you have distributions and thinking like bar graphs and things like that, when all the bars are all the same length as what you're seeing here, that's what we call a uniform distribution because everybody's the same. Over here, this is the one that we like to focus in on, and this is what we'll be focusing on the rest of this text or in 12.4. This is what we call symmetrical, or sometimes we call this a normal distribution. Okay, or we also call it bell shaped because it's looks like a bell. Okay, because usually bells go up and curve out. Okay, it's a bell shape. So this is what we call normal distribution, symmetrical, and this is what we as kind of professors, this is what we shoot for when we think about grades. We have, a few A's, a few F's, you get a couple more D's, a couple more B's, and then hopefully everyone's kind of in the middle average, right? So this is what we call a bell-shaped curve. Okay. Down here, these are what we call skew right, skew left. I know it seems like the names are backwards because you're like, the big hump over here is on the left side, Mr. Armstrong, and the big hump over here is on the right side. Why is this called skewed left, skewed right? Because when we talk about skewing, we're talking about the tail. See how we got this long tail? Where is that long tail at? It's over on the right hand side. Same thing over here. We got this tail. Where is that tail at? It's over here on the left-hand side. So when we talk about skew right, skew left, it's all about where is the tail at? And this is what we call the tail. And then another one that we got is what we call a U-shaped, okay? Where your bars, like sometimes your bars are heavy on the outside and then we're really low in the center, and then it starts to pick up again. So this is like tests where these people have studied really hard and they know the information, so they passed. These people didn't study really hard, they didn't know the information, so they flunked. So the test is, so this was like test data. It's like either you knew what was going on or you didn't. Okay, so kind of interesting. So some things I do want to kind of also mention in this when we talk about mean, median, and mode, back from 12.2, in a symmetrical distribution, what's really cool is that right through here in the middle, the mean, the median, and the mode all exist right there in the middle. Okay? So that's kind of really cool for symmetrical. And that's why we like to work with symmetrical data, or in other words, normal curves, because it allows us to know that the mean, the median, and the mode are right here in the middle. When it comes to skewing, well, obviously you can see that right here. That's the mode. Okay. Now the other two fall out like this. This guy ends up being the median. This guy ends up being the mean. So the reason why the mean is higher than the median is because remember the mean is the average of all your data. So what happens in skewed data is that you have outliers over here that are grabbing this mean and pulling it higher than what it should be. Okay, so that's generally when you get skewed data, is when you have outliers. So in this case, we have outliers that are very, very large, kind of like my number 24 in that data that you saw in 12.3. My number 24 was an outlier because it was much higher than the rest of the data. Okay, and again, median, it's the middle. So if you kind of like average both sides and work your way into well, not average, sorry. If you work your way into the middle from both sides, your median is between the mode and the mean. And on the skewed left, again, this is where the highest hump is, so that's the mode. And then again, the mean and the median work itself out like this, where again, this is the mean and this is the median. Again, the reason why the mean is so low is because you got those outliers that are extremely low in here. Okay. So when you have extremely low outliers and then everybody else is high, that's going to pull your mean down because of low. So that's like when I want to go and look at data, and if I look at information for, say, a class and their test values, if everyone has taken it but one person and everyone has scored, like 70s, 80s, and 90s, but I have one person that has a 0, that's a huge outlier there. That's going to pull my mean down for the class. The average for the class is much lower than what it should be. So outliers, like in skewed data, they will either pull your mean higher than what it should be or lower than what it should be. And again, we talk a lot more about that when you take STAT 2023. So let's talk about this symmetric distribution. So here you have notes that I have given you. Okay. And in these notes, they are called the empirical rule. And that's what this page is about. It is about what we call the empirical rule. And that's the big majority of this section. Okay? So the empirical rule says that between one standard deviation, and that's what this is, and this is your standard deviation right here. This is your mean. Okay? This is X bar. Between these two lines, within one standard deviation, you have 68% of your data. Okay? Between two standard deviations, 95% of my data exists. And then between three standard deviations, I have 99.7% of my data. Okay? So that's what the empirical rule is telling you, some basic information. So mostly when we say we're between three standard deviations, we say that is pretty much almost all of our data. That's what we generally we say. Okay. I want to explore this picture first and talk about some things that you might see in here. So with this information, we can actually break down and we could talk about distances between here. How much of my data is between the mean and one standard deviation? Well, again, remember that this is symmetrical. Okay. So if I want to know just this piece, well, I know between these two, it's made up of 68%. And again, this is symmetrical. So this is really like cutting my information in half. But what's half of 68? 34%. So that also means over here, this distance is 34%. You'll understand why we're talking about this soon enough, but I want you to have this information about, well, how much data is between these two? All right, so now the next guy. Well, how much of my data is in here? Between there. Well, again, all of this data in here is 95%. But remember, we've already taken care of this much of my data in here. How much is between these two lines? 68%. So if I take 95 minus 68, we get 27. So 27% is here and here. Okay, so 27% of my data is being made up between these two stretches of information. Okay? Well, just like before, remember this cuts our data in half. So half of the 27's here, half of the 27's there. 27 divided by 2. 13.5% of my data is between 1 standard deviation and 2 standard deviations. 13.5%. And then how much is down here in my last distance between 2 standard deviations and 3? Well, again, think about what's going on. This full distance is 99.7%. But between 2 standard deviations, I've already got 95% taken care of. So 99.7 minus 95 gives us 4.7. So between these two sides, 4.7 of my data lies. But again, it's cut in half. So half of the 4.7 is here. Half of the 4.7 is there. So 4.7 divided by 2 gives us 2.35%. 2.35%. So these are the percentages I want you to know about because they'll come in handy in some of our questions coming up. Okay? So keep that chart near you as we start working through this. Okay? So here we go. Let's talk about finding percentages of our data and talking about standard deviation and some things like that. All right? So it says, what is the score on a test that is half a standard deviation above a mean? Okay? So in this question, it's just having you do some little math. All right? So in order to do this, if you want to know what the score is, okay, that is a half standard deviation, what you're going to do is you will take the mean and you will either add or subtract. I'll tell you how you're going to know which one you're going to do. And you'll take the number times the standard deviation that you want to be. So in our case, the number is a half that we're talking about here. All right. Now, how do I know if I want to add or subtract? Well, if you want to add, you're going to be worried about being above. If we're going to subtract, then it's asking about being below. Okay? So when we look at our problem, it says we want to be above. So now we know what to do. All we're going to do is take our mean, which is 60, and we're going to add half the standard deviation, which is 12. And that will tell us what a score on a test is that is a half standard deviation above the mean. That's what it's looking for. Well, 60 plus, well, what's half of 12? That gives us 6, and 60 plus 6 is 66. And there you go. That's what this question is about. Okay? Using this little idea right here. All right. Try it again. And go. All right. So this time, if you notice, it says that we are below. So that means we're going to subtract. So 60 minus, what's our number we're dealing with this time? 3. Standard deviations is 12. So there we go. There's the mean, there's the number, because we want to be 3 standard deviations below. And the standard deviation is 12. So 60 minus 3 times 12 is 36. So what is 60 minus 36? We get 24. So that is a score on a test that is 3 standard deviations below the mean. Okay, so some of the questions in your homework are going to be just like that. They're going to give you the mean, they're going to give you the standard deviation, and then they want you to figure out what is the number that is 3 standard deviations below, or a half standard deviation above, or 1.5 standard deviations above. You know, it works just like that. That's all you have to do. All right, so now it's kind of changing things up. They want to know what are the percent of buyers who paid between 19,000 and 23,000. So this is where our chart is going to come in handy here. All right. So what I'm going to show you real quick is down below right here. I'm going to kind of make me a normal curve. Okay. And you know that in the middle of your normal curve, according to our chart, is X bar. Okay? And then we know that over here, this is 1 standard deviation above. And then over here, this is 1 standard deviation below. Okay? So the reason why we did those problems a couple seconds ago first, because you actually can figure out what's going on right here and here. Okay? Because they have given us information about the mean and they have given us information about the standard deviation. All right? So, if I want to figure out this first spot right here, I am 1 standard deviation above the mean. So if I want to figure this spot out right here, I need to take my mean plus 1 times the standard deviation. If I want to figure this spot out right here, I'm going to take the mean minus, because I'm below 1 standard deviation. This is just like what we did right here. Okay? We're just putting it back on that normal curve. And so right here, we know what the mean is. Up here, it says that the mean is $21,000. So if I go 1 standard deviation above that, well, all I'm really doing is taking 21,000 and I'm going to add 1 times 1,000. Well, 1 times 1,000 is 1,000. So what's 21,000 plus 1,000? 22,000. So if you are 1 standard deviation away, you are at 22,000. Well, right over here, all I'm going to do is take the mean minus 1 times the standard deviation. Well, 1 times the standard deviation, 1 times 1,000 is 1,000. So all I'm doing is taking 21,000 minus 1,000. So 21,000 minus 1,000 is 20,000. Are these the numbers that I'm looking for? No. We want 19,000, and 23,000. So maybe we jump out to 2 standard deviations. And again, you just repeat the process. This guy is going to be x bar minus 2 times the standard deviation. This will be x bar. Sorry, this should be plus because we're above. This will be x bar minus 2 times the standard deviation here. Okay? So, if you kind of think about this, all we had to do to get from here to here is 1,000. We're just going up another standard deviation. So if you didn't really want to take 21,000 plus 2 times 1,000, all you could have to do is really to get from one standard deviation to the next is add 1,000. That's another way of looking at this. So to get from here to here, we added 1,000. To get from one standard deviation to 2 standard deviations, add 1,000. It's another way of thinking about it. So at 2 standard deviations, we're at 23. Oops. About put 2,300. Silly me. $23,000 at 2 standard deviations. And again, over here, just like what we were talking about, if I add 1,000 going this direction, then I'll subtract 1,000 going this direction. So down here at negative 2 standard deviations or 2 standard deviations below, we're at 19,000. And these are the 2 numbers we're after. And according to our chart, how much of my data is between 2 standard deviations? If we go back and look at it, it is a total of 95% because we are between 2 standard deviations. That's 95%. And that's what they're looking for. Okay? They're just making you think about it in terms of the curve to find that percentage. All right. So the answer to this problem, 95%. That's as hard as what this stuff gets. Let's do it again. All right. So it says an IQ test is normally distributed with a mean of 100 and a standard deviation of 16. Find the percentage of those who score between 68 and 100. Go ahead, pause the video, give this a shot. It's just like what we did a second ago. And go. Okay. So I'm going to draw in my little... Well, that's horrible. There's my bell curve. We know that in the middle is the mean. So that is 100. Okay? So, looking at what we know, we want to be between 100 and 68. So, I'm already at 100 right here in the middle, so I don't want to go anywhere above. Okay? I want to focus in on below that because I want to get to 68. So I'm not going to go above 100 over here. I'm not going to be doing any of the adding of the standard deviation. Okay? What we're going to be dealing with is moving below the mean. Okay? Because we're already at 100. There's no sense in doing extra work over here. So if I go right next door to 1 standard deviation below, again, remember that all we're doing is taking the mean minus 1 times the standard deviation. That's how we're going to get this number. So 100 minus the standard deviation of 16. Because 1 times 16 is 16. So that tells us 1 standard deviation away is 84. Well, that's not the number we want. So let's go again over to the next one. So 2 standard deviations below. Okay. So if we're 2 standard deviations below, remember that that formula is x bar minus 2 times the standard deviation. That's where that guy comes from. Or again, as we talked about, you could subtract 16 and then subtract 16. And 84 minus 2 times 16 gives us 68. There's the number we're after. So they want to know how much is between here. This is why I talked about those other percentages on our picture, because they want us between -2 standard deviations and the mean. They want this distance. Well, what are the percentages that make that up? 13.5 and 34%. That's why I talked about all these other little pieces here, because sometimes we need those. Okay, so going back, so we know that this small little piece right here is 13.5%. We know that this piece right here is 34%. So what's 13.5 plus 34? That gives us 47.5% who scored between 68 and 100. Cool. All right. So in here, they're also going to talk about a Z-score. Z-scores are not hard to find. What Z-scores do, it allows us to kind of normalize the data into a unitless idea. Okay. So when you deal with standard deviations, a standard deviation is really kind of almost unitless. Okay. So this is one standard deviation. There's no unit on that. It's just a standard deviation. So this allows us to do a lot of comparison of datas and kind of gives them a value that doesn't really have a unit attached to it. Like the 84 has a unit attached to it. It's a person's score on an IQ test. This 100 has a a unit attached to it. It's how they scored. Over here, these units of 22,000, that's dollars. 21,000, that's dollars. What a z-score allows us to do is to strip all that away and talk about it in terms of just a plain number without a unit and do comparisons. Again, in statistics 2023, we talk a lot more about z-scores and we use z-scores a lot. Okay? So a z-score is the number of standard deviations above or below the mean a data value is. Okay? So it's turning your data value into a standard deviation number. Okay, again, it makes it unitless. And here's the formula for it. If you want the z-score, you're going to take the data item minus the mean and then divide it by the standard deviation, and that's your z-score. Super easy. The data value minus the mean divided by the standard deviation. So over here, I have given you the mean. I have given you the standard deviation, because remember that's what lowercase sigma is. So right here, this lower script right there, this is how we generally write z-scores. This lower script, that's the data value they want you to work with. So working this one right here, and then I'll let you do 64 on your own. Here's the data value, 48. We're going to subtract the mean from that, which is 60. And then we're going to take that answer divided by 8. Okay? So 48 minus 60 gives us -12. Divide by 8. And there will be no rounding on this. -12 divided by 8 gives us -1.5. So what that means for us is that a data value of 48 is 1.5 standard deviations below the mean. Okay, go ahead, pause the video and try number 64. Okay, so all you had to do was take 64 minus 60 divided by 8. 64 minus 60 is 4 divided by 8, and that's going to give you 0.5. And they do want them as decimals, no fractions on these. They do want decimals, no fractions. Okay, and I believe that wraps up 12.4. Oh, nope. Percentiles, this is just something to know. And you've seen a lot of this kind of information before, like when you take ACT, SATs, EOCs, things like that. Any kind of test, they usually tell you your percentile. So this is the definition of a percentile. So it says if n% of the items in the distribution are less than a particular item, then the item is in the nth percentile. Okay? So for instance, if I took a test and the test said that I am in the 84th percentile. Okay? That means 84% of people scored below me. Okay? 84% of the people were below me. That's what this is all talking about. Okay? So if they tell you that, another thing is that, say they said that 24% of the data is below you, then that means that you're in the 24th percentile. That's what this definition is saying. And that's what percentiles mean. It means that you can drop the word percentile and just call it a percent. That at that percent, everybody else was below you. Okay? So yeah, that's percentiles. Just wanted to bring that up because they do mention it in here. I don't believe you have any questions over this, but it's worth noting, and z-scores kind of relate directly to this. And again, you'll talk about z-scores more in 2023. And that is 12.4.